All right, so this video is to introduce you to sampling error and the sampling distribution of means. Now, before we get started, I need to give a disclaimer. This this is where it starts to get a little bit complicated, just in terms of conceptually. Okay, when we discuss the concepts that we're talking here, they're going to sound really new and confusing, and I understand that, but I want you to trust me to just continue powering through. I never expect that students are going to absolutely understand everything I'm introducing them to the first time I introduce them to it. That just doesn't, that's not how I think about what teaching requires. And so if it starts to get confusing, that's okay. Maybe it requires you to pause the video, come back to it later, take your time working through this material, but stick it out. All right. I just want to remind you to stick it out. All right. So let's discuss sampling error and the sampling distribution of means. So to begin with sampling error, we can expect some statistical difference between a sample and the population it's drawn from. In one of the previous videos, I mentioned the idea of me, wanting to understand the population of community college students in the United States. And I described how the bigger our sample, the better estimate that we can have that our sample is actually representative of the population. Now, what this means is then that any sample that we draw is going to be statistically different from the population that it comes from. So let's say, for example, the average age of community college students in the United States is, and I'm just throwing this out there, I'm not saying this is the case. Let's say it's 21 years old. That is the average age of community college students in the United States. If I draw a sample of 5,000 students from that population, it is very likely that my sample is not going to necessarily have an average age of 21 years old, okay? Because it's not the whole population. Any sample that I draw is just statistically unlikely to be an exact match to the population, all right? So when that happens, that difference between the sample and the population is called the sampling error. Okay? So it is the difference between the sample and its population. This means that the sample mean and standard deviation will unlikely ever exactly be the same as the population standard deviation. I should have also included population mean in here. Okay? So the sample mean and population, the sample that I draw, is very, very, very unlikely to be the same as the population mean and standard deviation. Okay, hopefully that kind of feels a little bit okay. I'm going to show you an example of this. So let's say that this table that I've just presented on the screen is representative of test scores, okay? And let's say this is my population of test scores. Now, I'm not expecting you to necessarily do the math. However, if you want to really solidify your understanding of this, it can be helpful to do the math as we're working through this particular section of this presentation. If you pause the video right now and add up all the numbers that are representative of this population of test scores and then divide by how many there are, the value that you should get the average test score should be 71.55. All right, that is the average of these test scores in this population. Now let's say I draw a sample from this population. In my sample, I'm taking scores from this, right? I just want to make sure that y'all are understanding that when I'm drawing a sample, it is a sample from the population. All right, so let me emphasize this point. Let's say this is my first sample. This is sample A. And in sample A, when I'm sampling this population, I pulled test scores 96, 99, 56, and 52. If these are truly representative of the population, what that means is that the values in this sample should be reflected in the population. And so again, if you pause the video here, you can find that the score of 96 is represented in our population. The score of 99 in sample A is part of the population of scores. 56 is represented and 52 is represented. Now remember, the sample is not going to be the same number of people as the population. So the idea isn't that I'm able to gather every single person from the population as part of my sample. My sample only includes 4 scores. Now when I take those scores and I add them together and divide by how many there are, I end up with a sample score of 75.75. And you can tell that 75.75, the mean of sample A, is not the same as the mean of the population. The mean of the population is 7155, right? So sample A is not exactly the same as the mean of sample A is not exactly the same as the mean of the population. What if we pulled another sample? Let's say this is sample B. Again, you could pause here, do the same thing. Notice that all of these scores in sample B are scores that have been pulled from the population. In sample B, you add up the scores, divide by how many there are, you get an average of 62.25. And again, this 62.25 is not the exact same as the population mean, okay? And finally, sample C did the same thing, 4 scores from the population, 7 years ago. I don't know why that popped into my head right now, I'm sorry. So sample C, we have 4 scores, add them together, divide by how many there are, we get an average for sample C of 68.25. That is not the exact same as the population mean, okay? So that is representative of the sampling error. That is the difference between our sample A and the population mean, or sample B and the population mean, or sample C and the population mean. Notice now that we are not talking about individual scores, right? We're not saying that we're only talking about this number 96 from this population. We're talking about drawing a sample from the population. And so samples, we have to keep in mind, are representative of a number of different scores, right? A sample is a smaller subset of scores from the population. All right, so